time travel has enchanted and intrigued us since the earliest days of fiction, when authors such as H.G. Wells, Samuel Madden, Charles Dickens and Enrique Gaspar y Rimbaud stretched and challenged our imaginations with images and tales of men and women who invented amazing machines and devices that could take them back in time, or forward into the future. Because of the restrictions of light speed, and the paradoxes of going back to the past without damaging the future timeline, and a host of other obstacles and challenges, we, in fact, have remained stuck in the present. Our scientific knowledge and technological achievement has yet to catch up to the limitless dreams of our imaginations. But perhaps just because we have yet to achieve time travel in our universe, in our particular point along the cosmic arrow of time, doesn't mean it isn't achievable, and maybe the key is the universe itself. Are we limiting ourselves to our understanding only of the laws and possibilities of our universe, and leaving out of the equation other realities, other universes, with other laws and forces, paradoxes and limitation, possibilities and potentialities, far beyond our own? In 2011, quantum physicists at the University of California at Santa Barbara, led by Andrew Cleland and John Martinis, designed a quantum machine, as they call it, that might one day lead to proof of time travel and parallel universes. Their machine, a tiny little teleporter barely visible to the naked eye, involves making a tiny metal paddle cool to its ground state, the lowest energy state permissible by the laws of quantum mechanics, and then raising its energy slowly by a single quantum to produce a purely quantum state of motion. They even were able to put the device in both states at once, so it vibrated both slowly and quickly at the same time, in another sort of Schrödinger's cat state of superposition. They posited that we can only see one of these potential states at once, and upon the act of observation, the state then splits into additional universes. Perhaps there is a plethora of multiple or parallel universes all around us, but we cannot see them. Wormholes could also be another possibility for teleportation, as physicist Max Tegmark suggested while attending a panel in January of 2008 at MIT to discuss the science behind the movie Jumper starring Hayden Christensen, about a man who can teleport all over the world at will. Tegmark, asked about the science behind the science fiction, remarked that a wormhole was one possible way of getting something quickly across spacetime. However, after admitting that wormholes do appear to be theoretically possible, Tegmark commented that the actual trip would be rather grueling because of the instability of the wormhole. It could collapse into a black hole, which would be kind of a bummer. Many scientists look to the possible existence of other levels of reality, or other universes, as a way to make time travel work outside of the restrictions of light speed and paradoxes. Imagine another universe alongside our own where the laws of physics are so completely different, that what is impossible here is mundane and trivial there. Multiple worlds, even, where each is different from the other, or perhaps an infinite number of universes where many would be exactly like our own. Hey, you might even exist in some of them just the way you are right now. In others, you might be rich, famous, handsome or even a cockroach. In fact, perhaps you might even be invisible in one of them. But we are getting away with ourselves here. When talk turns to the multiverse and other similar concepts, it's easy to start dreaming of science fiction worlds with every possible kind of life and all sorts of amazing machines and devices, and time travelers passing effortlessly back and forth between the past, present and future as if it were nothing more than a visit to a few Saturday morning garage sales. Parallel universes. Parallel universes have long been a mainstay of science fiction films and stories. Parallel universes can exist individually, or grouped together as the multiverse, and offer the possibility of a totally different reality in which someone, or something, can exist, or hop back and forth between. The laws of nature may be different in one parallel universe as they are in another, and in respect to time travel, would provide multiple versions of the future in which someone could exist, or not exist at all. Light speed limitations may not exist in a parallel universe, and the paradoxes that keep us from traveling back in time would be null and void if we could jump into a different historical timeline. Two great fictional examples of a parallel universe would be Alice's Adventures in Wonderland, written by English author Charles Lutwidge Dodgson under the pseudonym Lewis Carroll, and C.S. Lewis' The Chronicles of Narnia, both of which involve some sort of portal or wormhole, such as a rabbit hole or a large piece of furniture, through which a person can enter into another realm. Theoretically, parallel universes may be the result of a single random quantum event that branches off into an alternative universe. This is the many worlds interpretation, or MWI, of quantum mechanics, originally formulated by physicist Hugh Everett in 1957. It posits that each time a different choice is made at the quantum scale, a universe arises to accommodate that choice, thus creating infinite new worlds popping up all the time. These new worlds are being constantly created and could cause problems for a potential time traveler. Physicist David Deutsch wrote in Quantum Mechanics Near Closed-Time-like Curves for the 1991 Physical Review, that if time travel to the past were indeed possible, the many-worlds scenario would result in a time traveler ending up in a different branch of history than the one he departed from. Deutsch, of Oxford University, is a highly respected proponent of quantum theory, and suggests quantum theory does not forbid time travel, but rather sidesteps it, referring to the traveler's ability to go into another universe, a parallel universe, and avoid the paradox limitations. Deutsch's idea of parallel universes, the multiverse, or shadow universes, was described in his interview with The Guardian UK in June 2010. David Deutsch's multiverse carries us beyond the realm of imagination, as being coincident with, somehow contiguous with, and weakly interacting with this one. It is a composite, a layer cake, a palimpsest of universes very similar but not quite identical to each other. The number of these shadow universes could be enormous, and Deutsch points to photon experiments that suggest possibly a trillion of them or more. He also suggests that future-directed time travel will essentially only require efficient rockets, and is on the moderately distant but confidently foreseeable technological horizon. When it comes to past travel, the multiverse might save a time traveler from the pesky grandfather paradox. He uses an example of a writer who wants to go back in time with a copy of Shakespeare's complete works and help the bard complete Hamlet. It can happen, but in the multiverse view, the traveler has not come from the future of that copy of Shakespeare. Another offshoot of the MWI is the many minds interpretation, which extends the MWI by positing that the branching off of worlds occurs in the mind of the individual observer, introduced in 1995 by theoretical physicist H. Dieter Zeh, professor emeritus of the University of Heidelberg and the discoverer of decoherence. The many minds interpretation was widely criticized and somewhat ignored, mainly because of issues involving the theory that the mind can supervene on the physical as the mind has its own trans-temporal identity. The mind may select one identity as its own non-random reality, yet the universe as a whole remains unaffected, which presents additional problems when dealing with different observers ending up with the same measured realities. The actual process by which the mind of the observer would select the single, measured state is not explained by the MMI. Alternate timelines, each with their own forward arrow of time and their own history, may exist then, allowing time travelers to jump into another version of history and override those pesky paradoxes. Imagine being able to jump into a timeline where you do get your dream of marrying your high school sweetheart, but, finding out she's an evil tramp as soon as you say, "I do." You could jump back into your original historical timeline, where you didn't marry her and instead ended up 3 years later marrying her sister, your true soulmate, and lived happily ever after. Kaku's 3 ways to defeat the paradoxes of time travel. Noted theoretical physicist Michio Kaku, pictured below, author of Parallel Worlds and Hyperspace, writes in his newest book, Physics of the Impossible, a scientific exploration into the world of phasors, force fields, teleportation and time travel, of 3 ways around the paradoxes of time travel. The first is that you simply repeat past history and fulfill the past, and that everything you do once you are back in time was meant to happen anyway, a sort of destiny. This opinion is also mirrored in the views of famed physicist and superstring theory proponent Brian Greene, author of The Fabric of the Cosmos, Space, Time and the Texture of Reality and the Elegant Universe, Superstrings, Hidden Dimensions and the Quest for the Ultimate Theory. Greene writes that outside of the quantum world, in the classical science of the grander scale, we exist static and unchanging at various locations in what he calls the space-time loaf of block we call spacetime. These moments are unchangeable and fixed. Using a wormhole, if one were to indeed go back in time to a certain point, or date, one would find there is only one version of that date, and that your presence back in time would simply be a part of the original version of that moment. That moment has one incarnation, though. By passing through the wormhole today and going back to that earlier time you would be fulfilling your ironclad destiny to appear at that earlier moment. He points to the wormhole time machine itself as the culprit, with one opening or the other passing through time more slowly than the other end, but each opening is still going forward in time. Thus, there will also be a limit as to how far back in time you could travel in the first place. The second of Kaku's paths around the paradoxes involves having some free will to change the past, but within limits, so that you could go back and try to kill your grandfather, but something would prevent you from doing so. The gun might lock up, or you might drop it and shoot your foot instead and end up in the hospital. No matter what, you would somehow be prevented from knocking off your grandpappy. The third involves the universe splitting into two universes to accommodate the time traveler. His example offers someone going back in time to kill their parents, and in one timeline the people look like your parents, but are different because you exist in a different timeline. The many worlds approach could solve all the paradoxes in two ways. First, if we imagine the timeline of our universe as a line drawn on a board, then we can draw another line to represent the universe that branches off from the first. When you go back into the river of time, the river forks into two rivers, and one timeline becomes two timelines, and so on, and so on. Say you plan to kill your own father. You go back in time and you do the dirty deed. If the river of time does indeed have many forks, this would not be a problem. You've just killed somebody else's father. In that timeline, you don't exist, but you exist because you jumped the stream, Kaku writes. This idea would also solve another thorn in the side of physicists when discussing time travel, the radiation effects of entering a wormhole, which would no doubt destroy any time traveler, and also end up in a loop, the feedback becoming so strong it destroys the wormhole. If the radiation goes into the time machine, and is sent into the past, it then enters a new universe, it cannot re-enter the time machine again, and again, and again. Kaku points out that the main problems involving time travel and wormholes specifically center on the issues of the physics of the event horizon, as in the stability of the wormhole, the deadly radiation and the wormhole closing once it was entered. Solve those issues and time travel might be a piece of cake. Well, not a piece of cake. All physicists agree that once they come up with a theory of everything that unites the four universal forces of electromagnetism, gravity and the strong and weak nuclear forces, and formulate a complete theory of gravity and space-time, then time travel might be as close as finding a wormhole big enough, stable enough and open enough to get a time machine through. Not to mention the sheer amount of energy necessary to do this, which might require harnessing the power and energy of a neutron star, or finding that elusive exotic matter scientists are looking for, or a good source of negative energy, and we are far from doing any of these things. Oh, then there is the problem of creating the machine. And let's not forget finding or creating a wormhole that could handle it. An interesting problem was brought up by physicist and cosmologist Paul Davies, author of About Time, Einstein's Unfinished Revolution and other books. In an interview with Discovery.com called Is Time Travel Possible?, he discussed wormholes as time machines and potential time travel tourists from the future, but with the caveat that theoretically, it would take more than 100 years to create a 100-year time difference between the two ends of a wormhole, so there's no way that our descendants could come back and tell us we're wrong about this. So, it's all about timing, then, pun intended. The multiverse theory. The multiverse is the most widely mentioned theoretical time travel paradox killer, because it involves more than just one parallel universe, thus allowing for an increasingly possible world where the laws of physics are just right for time travel. If we can get from here to there, that is. There may be a massive number of other universes out there, possibly even an infinite number, or maybe just 20 or 70. While our astronomical observations cannot at this time detect them, it is most definitely a theoretical possibility that many cosmologists and physicists are considering. These universes may or may not be like ours. In fact, they may or may not even have the same laws of physics or distribution of matter, or even number of spatial and temporal dimensions. Some will undoubtedly be dead, and others will have life forms that we cannot recognize or even imagine. Others still may have duplicates of us living their own separate lives and timelines. Maybe, Big Bangs are going on constantly, the 24th of July 365, all the while creating new universes. The multiverse theory is not new, especially for readers of science fiction and fantasy, where other worlds beyond ours is a given. The actual term was coined in the year 1895 by psychologist and philosopher William James, and is now a mainstay of theoretical and quantum physics, as well as a part of our religious beliefs, mythological stories, and spiritual, New Age thought. The multiverse has been equated with everything from the kingdom of heaven of the Judeo-Christian Bible to the Akashic field or Hall of Records or various planes of existence of more metaphysical and spiritual thought, to the multiple timelines and dimensions of paranormal and anomalous concepts. Cosmologist Max Tegmark took the multiverse theory to the next level by creating a classification level for potential other worlds. Level 1, domains beyond our cosmological horizon, the least controversial type, what lies beyond the vantage point, yet likely has the same laws, constants, just with possibly different initial conditions than our own. Level 2, universes with different physical laws, constants, other post-inflation bubbles, far more diverse than level 1s. These bubbles also vary in initial conditions as well as other seemingly immutable aspects of nature. Level 3, quantum universes, many worlds interpretation, exist alongside us on the quantum level where the random quantum processes cause the universe to branch into multiple copies, one copy for each possible outcome. Level 4, ultimate ensemble, other mathematical structures, where all potential alternate realities can exist, anything and everything is possible in terms of location, cosmological properties, quantum states, and physical laws and constants. These exist outside of spacetime. Each level of multiverse has its own characteristics that separate it from the other levels, and for our purposes, the focus for time travel would be on those we humans could exist in, and possible travel between. One of the ways Tegmark differentiated the levels was by stating that in level 1 our doppelgangers could live somewhere else in three-dimensional space, but in level 3 they would live on another quantum branch in an infinite-dimensional Hilbert space. Yet, as the many worlds interpretation states, likely not be able to interact once the split into another branch occurs. Those found in level 2 might be like bubble universes that have different physical laws and constants, and each new bubble is created by splits that occur when spontaneous symmetry breaks occur in level 3. Tegmark describes these levels in detail in his book Universe or Multiverse, and states that the key question isn't so much whether there is a multiverse, but rather how many levels it has. He admits that nature may have tricked us into thinking our vantage point was the extent of reality, a fixed view of the world around us. Einstein taught us that space is not merely a boring static void, but a dynamic entity that can stretch the expanding universe, vibrate gravitational waves, and curve gravity. Many scientists refer to the multiverse as more of a pocket universe concept, indicating different regions in spacetime that are unobservable, but still a part of our one universe. Inflationary cosmology to state these pocket universes can be self-contained, with different laws of physics, different particles and forces and possibly even different dimensions. Even the popular string theory allows for potentially trillions of possible universes, each one compatible with relativity and quantum theory. Michio Kaku states in Physics of the Impossible that, normally communication between these universes is impossible. The atoms of our body are like flies trapped on flypaper. We can move freely about in 3 dimensions along our membrane universe, but we cannot leap off the universe into hyperspace, because we are glued onto our universe. Gravity, however, can freely float into the spaces between universes. Kaku also points to one theory where dark matter, which is an invisible form of matter surrounding our galaxy, might actually be normal matter in another universe. But the question remains, can we travel back and forth between these different worlds with different laws and arrows of time? Again, theoretically, it would require a shortcut through space and time, like a wormhole, and a means of safely getting through that wormhole should it be stable and traversable. So even though the multiverse theory takes care of some of the paradoxes by offering up alternate timelines and histories in which one can both go back to the past and kill their grandfather, while not killing him at the same time, it appears as though there is still no realistic way of actually doing that. The multiverse also allows for alternate futures as well, and for multiple, alternate versions of you to exist in any number of historical timelines with different outcomes depending on the choices you make in each baby bubble universe. In an article titled Riddles of the Multiverse for PBS.org's August 2011 Nova series, University of Southern California professor of physics and astronomy Clifford Johnson was asked straight out about whether or not the multiverse could ever be visited by humans. His response was that we must first work out the physics of these other universes, in order to determine when and whether it makes sense to cross over from one to the other. He did admit it is possible the stuff we are made of, the matter and forces that make us and hold us together, may not allow us to ever leave our 4-dimensional universe and go to another. Imagine doing so and well, coming undone. For now it seems we just don't yet have the brainpower and technology to leap and jump between worlds, to cross timelines and experience as many pasts, presents and futures as we would like. That knowledge and technology may exist, though, out there, somewhere in time. And if you want to learn more, I recommend you click the link in the description. From www.power-quadrant.blogspot.com/ and if you like this video, please give it a thumbs up and subscribe and share it with your friends on Facebook and Twitter and Google+. Thank you for watching and see you next time.